The internet kind of feels like magic, right? You click a link and boom, a web page from halfway across the world just appears. But behind that magic, there's this really elegant system called TCP/IP. It's the engine that's quietly powering everything we do online. So today, let's pull back the curtain and see how this thing really works. It really all comes down to this one question. How on earth does your request for, say, a website in London get to a server in Tokyo and then all the way back to you in what feels like an instant? Well, the answer isn't magic. It's just a masterpiece of engineering, and we're about to map out that entire journey. Okay, so to understand this journey, first you've got to learn the rules of the road. The entire internet, all of it, operates on a shared set of rules called the TCP/IP model. It's this invisible framework that makes sure every single device, from your phone to a giant server farm, is speaking the exact same language. At the heart of it all is this TCP/IP model. The absolute best way to picture it is as a stack of 4 layers, where each one has a super specific job to do. They work together in perfect order to get every single piece of data ready, send it off, and then receive it on the other side. This model truly is the engine of the internet. And here it is. This is our roadmap. We're going to follow a little piece of data as it travels down through these 4 layers on its way out to the internet. We'll start at the very top with the apps you use every single day and work our way all the way down to the actual physical wires and radio waves that carry the signal. So where does our data's journey begin? Well, funny enough, it's not out on the internet somewhere. It starts right inside your device. Before any information can go anywhere, it has to be created and then packaged up for the trip. And that's the whole job of these first 2 layers, application and transport. Everything kicks off right here at the application layer. When you open your web browser or send an email or stream a video, that application is creating the initial data, the actual message you want to send, and it hands it off to the layer below to get the packaging process started. And you actually interact with this layer all the time, even if you don't realize it. The rules that these apps use are called protocols. So HTTP is the protocol for the web, FTP is for moving files around, and SMTP is for sending email. They basically define the language your app uses to talk to another app on the other side of the world. All right, so the data's been created. Now it moves down 1 level to the transport layer. You could think of this layer like a shipping department. Its most important job is to pick the right kind of delivery service for the data that's being sent. And it basically has 2 main options. Think of TCP as certified mail. It's super reliable. It chops your data into numbered pieces, tracks every single one, and makes absolutely sure they all arrive in the right order. If one goes missing, it just asks for it again. UDP, on the other hand, that's more like bulk mail. It's way, way faster because it doesn't bother with all that tracking. It just sends the data and hopes for the best. And this is why, a tiny glitch in your video call is okay, but a single missing word in an important email is a disaster. It's all about using the right tool for the job. Okay, so our data has been packaged up for either reliability or speed. Now it's time to actually put an address on the package and send it out onto the digital freeways of the internet itself. The internet layer is basically the global post office for your data. Its main job is pretty simple. It stamps a source address and a destination address onto the packet. This tells all the routers across the world exactly where this data came from and exactly where it needs to end up. And that address is, of course, the IP address. You've probably heard of it. It's just a unique string of numbers that identifies your specific device on the global network, just like a street address identifies your house in a city. Without this, your data would just be lost in space. All right, we've made it to the final layer on the sending side, the network access layer. This is where the digital packet gets turned into a physical signal that can actually travel. It's like the bridge between the digital world inside your computer and the physical world of cables and airwaves. And this is that final step in action. Whether the data gets turned into radio waves for Wi-Fi, electrical signals for an Ethernet cable, or even little pulses of light for a fiber optic line, this layer handles that conversion. It turns all those digital bits and bytes into a physical signal ready for its big journey. So we've seen all 4 layers and what they do. Now for the really cool part. Let's put it all together and watch the entire round trip of a single data packet, from your click all the way to the server and back again.
So as the data moves down that stack, each layer wraps it in a new layer of information, which is called a header. This whole process is called encapsulation. The transport layer adds its TCP header for reliability, the internet layer adds its IP header for the address, and the network layer adds a final frame for the physical trip. It's kind of like our data is a letter being put inside multiple envelopes. Now it's fully packaged and ready to go. The data leaves your device and hits the internet. It literally hops from one router to the next, and each router reads that IP address, that outer envelope, to decide where to send it next, getting it one step closer to its final destination. And when the packet finally arrives at its destination, the exact opposite process happens. This is called decapsulation. Each layer strips off its own header. The physical frame gets removed, then the IP address header, then the TCP header, until all that's left is the original data from the application, ready to be used by the server. So you might be thinking, why go through all this trouble with layers and headers? Why not just send the data? Well, this layered system is precisely what makes the global, interconnected world that we all live in even possible. And this is the core idea right here. Because every device in the world, and I don't care who made it or what software it's running, agrees to follow these same four-layer rules, they can all communicate with each other seamlessly. TCP/IP is the Internet's universal language. The power of having this shared language gives us everything. It guarantees global interoperability. A phone in one country can talk to a server in another, no problem. It gives us flexibility, because you can swap out your Wi-Fi for a cable without messing up the other layers. And with protocols like TCP, it gives us guaranteed reliability for our most important data. And just try to wrap your head around the scale of it all. This isn't just about a few computers. We're talking about over 5 billion people and tens of billions of devices, all connected and all communicating using this one, single, elegant set of rules. The scale is just mind-boggling. So, the next time you tap your phone or click your mouse or stream a show, just remember what's happening underneath it all. It's this beautifully simple but incredibly powerful system of 4 layers, all working in perfect harmony, moving countless packets across the globe every single second to keep our digital world running. And that brings us to a final thought, a question to chew on. We've perfected this amazing, universal language for moving data packages around the world. But what happens as the content of those packages, the data itself, gets more and more intelligent? What do you think is the next layer we're all going to build on top of this incredible foundation?